Well, hello everybody, and first of all, I want to say it's an honor to be here as part of the Mars Society Convention. I'm already one member of the tribe because I'm a member of Mars Society. I'm very passionate about the red planet Mars. I'm very passionate about expanding human space exploration and definitely colonization of a new world planet, and specifically, of course, with Mars. But one thing I am not passionate about is to land on Mars and become two blind eyeballs and a pile of heap of skin, which actually could be a reality scenario if we do not find a way to countermeasure mitigation technology to be able to help us survive on the long duration to Mars and also for eventual colonization. So what I'm going to present here is a technology that addresses the physiological deconditioning of space specifically for long duration missions in deep space and also for colonization of Mars. So the title is Mars Mission, Survival and Colonization Using an Integrated Multi-System Countermeasure Hardware Technology, specifically the Gravity Loading Countermeasure Skin Suit, which is a mouthful, so we call it the GLCS. Mark III, which is a terminology, really basically is a prototype 3. So we've already really worked on the concept, building it for the last 4 or 5 years, and now it's actually prototype 3, working on to evolve it to prototype 4. So you can see this is a multidisciplinary team, an international consortium consisting of King's at the CHAPS, which stands for Center for Human Aerospace Physiological Sciences, MIT at the Manned Vehicle Laboratory, Ames, NASA Ames, let's go back. There you go. NASA Ames Research Center, funded by Wiley Labs of Europe, and of course, European Space Agency and the National Space Biomedical Research Institute. So part of the research team for my study is, including myself, is Dr. Newman, who is at Harvard MIT, Director of MIT Technology and Policy Program, Dr. David Green at King's College London at CHAPS, who's the Director of Space Physiology and Health, co-chair of the UK Space Biomedical Association, Dr. Yvonne Kago, who is also a NASA astronaut, flight surgeon at NASA Ames and faculty at Singularity University at Silicon Valley, and Susanna Zanello at NASA Johnson Space Center, the University Space Research Association, and the PI of HERO, which stands for Human Exploration Research Analog and Bed Rest Studies. So for me, a little bit about my background, what motivates me, why I'm so passionate and committed to finding the capabilities to enable us to actually go to a planet, Mars, and to literally be able to survive there, because I don't want to go there and just die. I want to go there, colonize it, and be the first pioneers, you know, and actually also to increase the capability of us becoming interplanetary species. So, of course, the people that actually motivate me, I'm just going to talk very quickly because I have lack of time, is Neil Armstrong, and I actually watched him step on the moon when I was very young, and his one small step for man and one giant leap for mankind. I thought, God, that's great, because probably within the next 15, 20 years, we'll be living on a planet. Obviously, that didn't happen. Of course, I thought Buzz was here, but so I made this for him. I thought this is great, because there you have Back to the Future, Buzz back then, and then somebody put an iPad and iPhone, so I thought that's great. Back to the Future Buzz. And of course, this is my dad, Ip Kwong Lo, who really motivates me, and I'm part of who I am today, and why I'm so passionate is because he also is a pioneer and visionary. He was part of the Chindits of 3,000 men under General Ord Wingate, became the first and only Chinese to become this member of the SAS, which is Special Air Service, which are the elites of the elites. These are the precursors, the forefathers of special ops and special operations that we know today. But what I want to say to you is what instilled in me was the motto of never give up, of the SAS, and who dares win. So I dare that we will one day colonize Mars. And of course, here we have templates for human Martians, which I totally believe, and Mr. Spock is my hero, and one day maybe we can even find a way to do mind melt. And so I won't have to be able to, you know, have to spend 30 minutes to tell you my presentation. I can just touch you and go, yes, and you get it. Oh, what happened? So where's the mind melt? Can somebody figure out what happened? Oh, it went to sleep. So, of course, Ziggy Stardust and Spiders from Mars, David Bowie. here is, and Chris Hadfield, you know, when he actually did a cover of Space Oddity from David Bowie and brought on 12 million viewers to, so this is actually a whole new generation of space enthusiasts. So why go to Mars? Well, for all these reasons: colonization, new world, new discoveries, technology, innovation, terrestrial spin-off, improved quality of life on Earth, evolution, humanity, of course STEM, outreach, inspire next generation. But for me, the main thing for me is to become a multiplanetary species and of course become a Martian citizen. If I have time at the end, I'll show you a wonderful Mars video. So I want to show you this slide. I'm not going to go through it all because I don't have time. But basically the takeaway point is that space affects all systems in the human body, which makes sense because we are an organism that's an integrated multi-system organism. So what affects one system has rippling effect with all the systems in our body, and that is actually the case what we find with all the astronauts to date. So I'm going to give you a quick, first one, let me ask, anybody has medical background? Okay, so I'm going to give you a quick medical school lecture 101 and really go through some of the major physiological deconditioning of space. And this actually is very important because even though people are saying, okay, you can, you know, incorporate artificial gravity and then that will get us to there, but what about when we land and we want to live on Mars? You know, artificial gravity? So that's a question to think about. So some of the physiological deconditioning, some of the main problems is cephalary, which basically in the lay term means fluid going towards the head. So cephalic fluid shift, bone loss is a major problem, muscle atrophy, which is muscle wasting, deconditioning, legs, feet gets affected, stomach, spine, molecular damage. So let's talk with cephalic fluid shift because actually one of the major problems, I think, it's one of the central problems that's causing all these other secondary problems with the body, physiologically. So let's go to the next slide to better explain this. So this slide is actually pretty good because it's showing you in A, this person is normal under one Earth gravity, so normal distribution, we're evolved to live under one Earth. Here in B, is an astronaut actually in low Earth orbit. This is all data from lower Earth orbit, so it's not even deep space. But this is a person, an astronaut, maybe 1 day to 2 weeks, and then C is initial fluid shift in space, C in, goodness gracious. I'm showing you this. Why is this going back? Sorry. So C actually is showing you fluid, oh goodness. I don't know why this is doing this. Okay. So anyway, C is fluid shift resulting from long duration space flight, and this is, most of the data was accumulated during the space shuttle missions. So this is between like 1 month to 4 months to 6 months. And you can see that most fluid shifts are heading towards the head. And then, of course, when you come back into 1G of Earth, then you get the opposite effect, when the 1G forces all your fluid down towards your feet, and then you get what we called orthostatic hypotension, so you get the imbalance, you get the gait, and so on and so forth. So the other thing is bone loss. So bone loss is actually a major problem. And what happens is that when you take away that 1G of Earth, that loading force, it causes calcium to leach, what we call resorb out of your bone. It comes out of your bone into your circulation. That causes a lot of problems. One of them is kidney stones, because it's filtered through the kidney, accumulates, the calcium accumulates in the kidney, and then you get the stones. The other thing it causes, because you're going to leach the calcium out of your bone, and because you've lost the force, that loading force on your bone, on your major anti-gravity bones, then you're going to get premature osteoporosis. And data has shown that there's a loss of 2% of muscle mass per week and the loss of bone density of 1% per month. Then what I think is interesting is, so studies have shown that on astronauts that have been rehabilitated, that even when the bones are reformed, it's reformed abnormally. In other words, it's more weaker, it's more brittle. So muscle atrophy as well, muscle wasting, deconditioning, so decreased strength and fitness. It affects the legs and feet, decreased loss of sensory and proprioception, so you can't feel, you get paralysis, so on and so forth. Stomach, of course, decreased peristalsis, motility, as well as mobility, of course, because digestion stops or slows down. Then this is also one of the major problems, severe back problem that's caused by elongation of the spine. So astronauts have come back in low Earth orbit after 6 months to a year, and their spine actually elongated 2 to 3 inches. So molecular damage, of course, which we already know about. And I just want to show you quickly, because I know my time is running out, is that this graph is actually showing you bone mineral density. Oh my goodness. Okay. It's showing bone mineral density change after 4 to 14.4 months of space flight. So it's representing a percentage change per month. And just really showing you here is the bone mineral density of all the different sites they looked at, from spine to arm, leg. And here is the percentage change per month, is to look at here that on average they lose 0.35% change per month of bone mineral density. And then here is the graph that actually shows you all the studies put together, and this is spaceflight data on structural alteration of anti-gravity muscles. So anti-gravity muscles are your triceps, your quadriceps, your plantar flexor, your calf, your knee extensor, your glutes, your quads, your calf, your thighs, and so on and so forth. But just a quick looking at this one, because this is 180 days in space in low Earth orbit, and here is 115 to 197 days, looking at the quads and gastrocnemius and the soleus, which is back here. And on average, they're losing, in terms of decreased volume and cross-sectional area is around 12 to 24 and 20. So that's literally quite significant loss of muscle. So for those of the lay people, I'll put this up because I do K-12 education too. So this really summarizes what I call the SpongeBob effect of space. Literally, that's what you're seeing. You're seeing your bone become more spongy and soft. You've got the vision problems, the bulging eyes, retinal detachment, blindness possibility as well. That's what is the scenario. Of course, you're going to get the chicken legs and the skinny arms. That's one of the effects. And this is data just for a short duration mission. What about long duration? You know, Inspiration Mars and then colonization, the psychological factors that I'm not going to discuss today. Of course, recently, the National Academy on Human Spaceflight did a review, and one of the conclusions they came out with, I think, is one of the problems of how we approach countermeasure mitigation strategies, that we're doing it from a stovepipe approach. And if we do that, and we're looking at all these different countermeasure programs that are currently under study, nutrition, bone, and vision, it really would require to really get a positive effect of mitigation is to the astronaut needs to use 80% of every day to be able to get the benefits of those countermeasures. So that's a problem. So here's an example of what's happened, how they try to mitigate against bone loss, bone atrophy, and they do a lot of exercise. In fact, exercise. In fact, they exercise 2.5 hours a day, every day. And it's still very ineffective. It's only 35–40% effective. And not only that, if you have to look, you look at the exercise devices. This is the ARID. You can see how cumbersome, how large it is. They have to wear straps to keep them down, to be able to, so they don't float away. And there's very high non-compliance. In other words, they don't like using it because it's quite painful after 2 hours being strapped down. And then, of course, when you're looking at deep space exploration, when you're looking at payload, this is not a feasible or viable way to be able to mitigate against bone loss and bone muscle atrophy. So what's the problem? The problem, as I said, is that we're looking at the whole problem. We're looking at the entire system, not as an integrated, holistic approach, but we compartmentalize it and then rendering that problem, those problems ineffective. So the truth is, this was taken by Transhumanism from Max Igor, and the truth is that this is all done by design because in addressing their respective symptoms, people are trained in each of their different specialty discipline. They're trained to believe they have to work within the parameters of that specific system rather than addressing the actual root of the problem. So what is the solution? First of all, what is the problem? The main problem that's causing all these deconditioning. Well, I love Mr. Spock. It's my favorite because he's very logical. He says, well, Captain is quite logical. Because so here's a balance equation, x plus y equals z. If you take out one of the components, Like in the space matrix, you remove the 1G component, then you're going to get imbalance. So what's the most common logical sense and how to resolve that problem? You put the 1G back. And also, you need to think that we're looking at a new paradigm. We're talking about new matrix. We're talking about traveling in deep space. We're talking about colonization of a new world. So this is a new matrix that we need to think about. So therefore, for the new matrix, you need to think about new paradigms and new concepts that fits that new matrix. You cannot, what I'm saying now, you cannot really use the Apollo paradigm because that's an old technology, an old matrix. Well, it's the matrix of Earth. So, in terms of the spacesuit design paradigm for long-duration missions, for Mars colonization, what we need to do is we need to change, disrupt, eliminate the existing gas-pressurized spacesuit paradigm. We need to create spacesuit technologies that allow humans to survive, live, work, colonize in low Earth orbit because space tourism will come online within the next 5 years to 10 years. Well, I would say 5 years. Long duration, deep space, Mars, planetary new worlds. So what do you need to do? You need to design next generation spacesuits that are totally integrated systems. In other words, it needs to have not only physical protection, vital life support system. This is important too. You need to also integrate a countermeasure mitigation technology or platforms that actually address the physiological deconditioning of space. So this is really just reiterating what I just said, but for astronauts, humans to explore deep space, eventual planetary colonization, the spacesuits must be sleeker, smarter, flexible, maneuverable, and integrating a total system with real-time biometric monitoring, televirtual medicine, including integration of this countermeasure technology. So the new paradigm we are working on is building and developing the next generation skin suits, or we call skin. And this new paradigm is using not gas pressurization, but we're using integrated countermeasure, mechanical counterpressure. So I want to show you this, but this isn't what I'm going to talk about, because this is actually Darwin Newman, who is actually she's the head PI of the study. But she came up 4 years ago. This is old technology. This is the biosuit for EVA, for outside extravehicular activity. So she designed this biosuit using the integrated mechanical countermeasure. But I wanted to show you this because I want to show you, without me having to really emphasize what I just said, the difference between the Apollo suits, the gas pressurized, which does not obviously work in deep space, and also colonization. Whereas this, the skins, and of course she's, in the last 3-4 years, has actually evolved. And if I have time, I'll show you what she's been doing with the biosuit. So what I want to talk about is the development of the IVA, which is in intravehicular activity. In other words, you wear the suit inside a pressurized environment. So that would be either in the space capsule going to Mars, or of course when you're living on Mars, colonized, you live in the biodomes or the habitats on Mars. And remember that this suit, that this GLCS, it's a countermeasure mitigation technology that is addressing the medical physiological deconditioning. So I anticipate that within the next 5 to 20 years, humans will be actually in all these environments, low Earth orbit, of course, the space mining, which we already heard from Planetary Resources. Of course, Bigelow, with aerospace inflatables, will have space cities specifically in low Earth orbit, first of all, for space tourism. Of course, the lunar baseport, and here's Mars, and planet colonization. So I want to show you this because this happened recently and really emphasize what I'm saying, why the Apollo gas pressurization suits do not work. Here you have one of the astronauts. He had a water leakage in his helmet, and he had to be brought in. And when he was in, he couldn't take it off himself. So he literally had to have all the astronauts help him to take off his helmet so he doesn't drown in his helmet, and also to get him outside the spacesuit. So we can see this is absolutely not the paradigm for deep space and for colonization of a new world. Here I'm showing you what the skins can do. You can see this is the skin suit actually allows for self-donning and doffing. That's the terminology for astronauts. Really means donning, means you're putting on the spacesuit, doffing, you're taking it off. And then here you can see on the right, this is the actual GLCS when you're not wearing it. You can see it's light and portable. You can throw it in your backpack. You can wash it a couple of times, so on and so forth. So my research objective is NASA actually has a crew health risk mitigation directorate for human performance and operational readiness need for technology, what they call the technology readiness level, TRL, to address all these issues for long duration mission. So what I want to do, in terms of my objective of the research, is to further develop this technology, to optimize it, to validate it. I'm going to be the lead for the biomarkers molecular study for the technology, and then we want to also develop the spacecraft, plus the development of the spacecraft concept, which I will talk to you in a minute. So what is the TRL? I'm not going to have time to be able to go through it, but you can go on NASA site and Google TRL. But basically, TRL1 is just a scale for them to see how advanced where you are with your technology or your concept. So TRL1 is basic principles or technology observed and reported, and all the way down to 9. 9 is actual system proven or technology proven through successful operation. So you're actually using it in a system. So right now, our technology is at TRL6. So my hypothesis for this coming proposal is that the hypothesis you wearing or donning the GLCS M3 can be used as a novel multi-system platform, and we're going to actually test the technology in a G-transitional environments, in gravitational environments. In other words, in zero gravity, we'll test it in hypergravity, also in parabolic, suborbital, and of course the ISS. Hopefully within the next 12 months that we'll be able to get on the ISS. And then terrestrial-based analogs, of course, high seas, which is the current we just actually finished a few days ago, which is the Hawaii Space Exploration Analog Simulation, of course, Antarctica and NDRS. Deep space missions for asteroids, Inspiration Mars, colonization, of course. And the whole point of this is to be able to show that they can enhance physical performance capabilities, increase fitness, strength, and wellness. My hypothesis, too, is developing the concept of the space skin or the exoskin, and this is really applying on top of wearing the skin suit. We're going to apply an isolated, localized pressure cuff, which is a modified pressure cuff, and show that will further enhance the physical performance and capabilities of the skin suit. So when you wear that, besides wearing the skin suit, you're wearing this modified exocuff, and it actually enhances the performance. So these can be actually additional. So my goal also, not only for space exploration and colonization, I'm also interested in developing, creating terrestrial spin-offs so that we can improve the quality of life on Earth. And one of the spin-offs of this is we can actually use this technology and help patients with, for example, musculoskeletal conditions, cerebral palsy, chronic bedridden conditions, for example, multiple sclerosis, and also use it for training athletes and super fit athletes for the Olympics. Okay, so here is the crust of the main concept and design of the GLCS. This is the initial prototype that was came up with Dr. Newman and Dr. Waldy about 4 years ago, and the idea, it is not the Russian pinfin suit, but the idea came from this. So what is the Russian pinfin suit? Before I talk about this, the evolution of the GLCS. So here you have the Russian pinfin suit. What they've done is they've loaded all the force only into the midriff here, in the waist area, and they used bungee cords, went over the shoulders, and then bungee cords from the waist down to the ankles. The problem with this, of course, is that you're not getting an even distribution of the loading force over the body, the musculoskeletal skeleton, and also all the weight and all the force is there in the midriff, so it's causing a lot of pain. You can't really wear it for long. It's intolerable to wear. So what happened was that Dr. Waldy and Dr. Newman took that idea, the initial idea, using MATLAB, bioengineering, biomechanics algorithms, and body movement simulation software. They took this idea and they they put this loading force, they gradually applied the loading force evenly along the longitude axis of the skeleton from the neck down to the ankles, so that there's this more of an even distribution of the force on the musculoskeletal skeleton, and so that this actually is more realistic and mimics that 1G earth force on the body. So basically, you're replacing that 1G. So here you could see the design. Here's the key horizontal landmarks used along the body as you traverse from the neck down to the ankles. And here, these landmarks are to calculate appropriate loading, material strain, and use as reference points for vertical measurements. So it's made out of Kevlar, but we're integrating advanced nano materials. It's also bidirectional. This circumferential is higher, it's stiffer, so you prevent slippage. It's customized for individual as well, and then it can go up in size because it's actually quite stretchy. So I want to show you this, and this is a graph, actually, here, the XY, here's the height, here is the G loading force on the body, and here you can see this is the penguin suit where most of the force is here at the midriff here, but whereas the GLCS, the initial prototype, it mimics the force loading on the body as the Earth gravity. And here you could see the evolution of the GLCS. This is the initial prototype. This is Mark II. What they found that they couldn't maintain the 1G force in the initial prototype, so they added more compression here on the lower part of the anatomy, and then they evolved it more to the current Mark III, where they added a stirrup and actually be able to maintain a 0.9 GZ loading, and also they modified the area here to make it more comfortable. So, because of lack of time, if you want to talk, I will talk to you out there if you want to find out how we're going to develop the space cuff. So here I want to show you what they've done with testing. They use aerobic and resistance exercise with the GLCS Mark III, and also they used ergometry. They tested in upright ergometry and recumbent ergometry, and here, to maintain the GC loading, they put the stirrups right under the pedals. So some of the main data that's been I've tabulated, which I'm going to just show you the Mark III, is that here was done at CHAPS, Wiley and European Space Agent funded. And Carville, Green, and Waldy Evitz were the main PIs. So they looked at resistance exercise. They wanted to validate the validity of it, the viability, tolerability. So they validated that they can maintain a 0.85 GZ, that there was viable movement wearing the technology. There was attenuation of range of movement compared to normal, which was expected. There was thermal tolerance. Another study currently that's undergoing is looking at the fluid shift. So that will be interesting using the tilt table. Tilt table is when you're lying horizontal, it actually mimics zero gravity. So you get the same effects of deconditioning on Earth if you're lying for a long period of time horizontal or at 6-degree head down tilt. So some of the key findings, as I will want to show you, is that it actually performs well. There's a high state of readiness for further testing to determine its efficacy, and it showed a high fidelity to 1G within the testing structure. Self-donning duffing of the suit became easier, and there was normal range of motion, and it was found to preserve even when you're wearing it in the upright and recumbent ergometry exercises. And some other key findings, both upright and recumbent ergometry, at 75% VO2 max were possible within the GLCS. And then here, the leg press, which is interesting as well, it increased heart rate, and that suggests some cardiovascular impact. So some recommendations which I will incorporate into my study is modifying the SIP to incorporate a stretch monitor within the suit. Then we'll have the ability to titrate the G loading on the suit. So of course, it'll be interesting because Mars is 1/3 of the Earth gravity, the Moon is 1/8. So we will have that ability to test these different GCs by being able to add the stretch monitors into the zipper area. Of course, further investigation of the suit in different environments, which is what I'm going to be doing, and also testing of prolonged wear, which is important, its tolerability and effects on the spine. And let's see. So just quickly, I know I've got like 30 seconds. These are the analogs we're going to test it in. Here is the head down tilt I was talking to you about. This mimics microgravity. Here's one of the, at the University of San Diego. Here they actually developed the hypergravity using the spin cycle to be able to mimic hypergravity. There's the long arm centrifuge at the Ames, which we'll be using. And then, of course, in all these different environments, suborbital using Virgin Galactic, and then of course one day to be able to use the SpaceX Dragon and do long duration missions. Here of course the terrestrial analogs we're going to test it in, and my hope is that one day that we could actually incorporate this technology and test it in the Inspiration Mars, because I know it's 501 days, but 536 days. And eventually, of course, if we're successful with colonization with the Mars One project, then that will be actually a wonderful test bed to be able to use this technology. And here, we're actually going to be using, to get all the biometrics, in other words, to be able to get monitor real-time temperature, respiration, blood oxygenation, heart rate, blood pressure, and even stress. We're going to use this, actually just came out, and it was a team from part of X Prize, the Singularity University in Ames, Silicon Valley there. It's called the Scanadu Scout. It's literally like the tricorder. You wipe it on your forehead, you get real-time biometrics, and it's wireless. So, okay, so I don't have time, run out of time, but just want to say one thing is that one of the vision of where we want to go is to integrate the biosuit and the GLCS technology so that you'll get this idea of a dinosuit skin concept, where everything is integrated into the skin. And here's the integrated deep space skin suit that actually was presented at Cologne in Germany at the Human in Space, of what DARPA's doing with the biosuit. This is actually the space helmet. There's a person behind that you can't see, but he literally is using a voice command activated displays, kind of like the Google glasses. Okay, so I don't have time to talk about what DARPA's doing, the biosuit, but if you want to know more, then you can come and talk to me about it. So of course, these are the space pioneers pushing the envelope. And here I was working for the last few years, working on developing virtual clinic. And here you could see the experimenting with developing the holodeck. And here is the Bigelow, of course, all the inflatables. That actually, here's the real life-size model there in their site. And this is where the future of inflatables would go, especially in the low Earth orbit. This is a space clinic that they're already looking at and developing. These are the modules. They put several modules together. And then here, just a shout out for astronauts for hire, because of the commercial space sector coming online. There's a nascent industry for commercial astronauts that are really highly trained, and they train at NASTAR, the Sirius Astronaut Training Center. And if you want to know more, you can Google astronaut for hire. And here I am with I'm training as well, so as a commercial astronaut. And there's a team there, and I'm on the X-Core mock-up. And of course, you know about that. And here I want to say, let me just leave you with this. So of course, SAS motto, who dares win? But I want to leave you with Cecil Beaton saying, you are to be daring, be different, be impractical, be anything that will assert integrity of purpose and imagination, imaginative vision against the play-it-safers, the creatures of the commonplace, the slaves of the ordinary. So I say to you, don't just be ordinary, be extraordinary. Don't just be terrestrial, be extraterrestrial. And hey, let's occupy Mars. And hey, look, if Barbie's going, I'm going to go. So I hope you join us. Thank you so much.
Thank you, Dr. Jewell.
Sorry, I took the time.
Next up, we have Dr. Hanley with the need to develop radiation treatment sophistication.